Another important configuration for waveguides is circular waveguide. Circular waveguide has a cylindrical shape of circular cross section. The circular cross section has a radius A, and it assumes that the waveguide extends along the z direction. So any point inside the waveguide can be represented in cylindrical coordinates in terms of the radius rho and the angle phi from the x-axis and the length z along the longitudinal direction. In the case of circular waveguide, the transverse field components are E rho, E phi, H rho, and H phi. In a similar way to the rectangular waveguide, we can represent the transverse field components in terms of the longitudinal field components. The longitudinal field components are Ez and Hz. And similar to the case of rectangular waveguides, if I'm talking about E rho, so in terms of Ez, it would be the proportional to the derivative with respect to rho. Similarly, if I'm talking about E phi in terms of Ez, it would be proportional to the derivative with respect to phi. But should be noted here, the derivative with respect to phi cannot be with respect to phi only. It is usually 1 over rho partial by partial phi. Okay. On the other hand, if I'm talking about H rho in terms of Ez, it would be proportional to the derivative with respect to phi. So it would be 1 over rho partial by partial phi Ez. And H phi in terms of longitudinal electric field Ez is proportional to partial by partial rho. For the case of electric field from electric field, the proportionality constant is minus j beta over kc squared. And actually this is the same for both rectangular and cylindrical. And for magnetic field from longitudinal electric field, the proportionality factor is j omega epsilon over kc squared. On the other hand, if we are talking about the electric field from the longitudinal magnetic field, the electric field in rho direction would be proportional to the derivative of the magnetic field in the longitudinal direction with respect to phi. If this is rho, this would be phi. And as I mentioned, the derivative with respect to phi should be combined by 1 over rho. So 1 over rho partial by partial phi. The electric field in direction phi in terms of the longitudinal magnetic field Hz would be proportional to partial by partial rho. On the other hand, if I'm talking about magnetic field from magnetic field, it would be in the same direction. So in this case, if I'm talking about H rho, it would be proportional to partial by partial rho Hz. And if I'm talking about H phi, in terms of Hz, it would be 1 over rho partial by partial phi Hz. For the case of electric field from magnetic field, the proportionality constant is minus j omega mu over kc squared. On the other hand, for magnetic field from magnetic field, the proportionality constant would be minus j beta over kc squared. Now, if you are assuming that Ez equals 0, this would be transverse electric field component or transverse electric field modes. If I'm assuming Hz equals 0, this would be transverse magnetic modes. We are going to start with transverse electric modes. In transverse electric modes, Ez would be 0. In this case, the wave equation would be solved for the longitudinal magnetic field component Hz, and from Hz we can obtain the transverse field components E rho, E phi, H rho, and H phi. By assuming that Hz is propagating in forward z direction, so the field dependence on z, it would be e to the power minus j beta z, while the field dependence on rho and phi would correspond to the mode distribution of Hz. Now, it is required to determine the mode equation Hz as a function of rho and phi. By assuming forward propagating function, the derivative with respect to z will correspond to multiplication by minus j beta. So the second derivative would correspond to minus beta squared. And the value of k squared minus beta squared would be defined as kc squared. As here, k squared minus beta squared would be defined as kc squared. So in this case, the wave equation, or the Helmholtz wave equation for forward propagating waves inside a circular waveguide can be represented in cylindrical coordinates as partial by partial rho squared plus 1 over rho partial by partial rho plus 1 over rho squared partial squared by partial phi squared plus kc squared. Actually, this kc squared is k plus partial by partial z squared, and partial by partial z squared is minus beta squared. So k squared minus beta squared is kc squared multiplied by hz as a function of rho and phi equals 0. Effectively, these three terms correspond to nabla t squared in the case of cylindrical coordinates. By following up similar steps to the case of rectangular waveguide, we are going to use separation of variables. In this case, hz as a function of rho and phi is assumed to be the multiplication of two functions, r as a function of rho multiplied by b as a function of phi. So in this case, the derivative of hz with respect to rho will correspond to the derivative of r with respect to rho while b is constant. On the other hand, the derivative of hz with respect to phi would correspond to the derivative of b with respect to phi while r is constant. Now, by applying this form in this differential operator, it will correspond to r partial by partial rho squared, b multiplied by partial rho squared r plus b multiplied by 1 over rho partial by partial rho r plus r multiplied by 1 over rho squared partial squared by partial phi squared b plus kc squared r multiplied by b. This equals 0. Now, by dividing both sides by r multiplied by b, we can obtain that 1 over r partial or d squared r by d rho squared plus 1 over rho r dr by d rho plus 1 over rho squared b d squared b by d phi squared plus kc squared equals 0. As we said in the case of rectangular waveguide, we can note that this part is function of rho only, while this part is function of phi only, and this is constant. And to make these parts together equal 0 for any rho and any phi, this means that this value should be a constant value, this value should be another constant value, and this constant value plus this constant value plus this constant value equals 0. Or in other words, we can say that 1 over r, we are going to multiply both sides by rho squared, such that this would be completely function of phi. So in this case, this would be rho squared over r d squared r by d rho squared plus rho, because this rho squared over rho, it would be rho over r dr over d rho plus kc squared multiplied by rho squared. This should equal negative of 1 over rho over b partial squared b by partial phi squared. And this is function only of rho, and this is function only of phi. And to make this function, this value always equal this value for any rho and any phi, they should have a constant value. Let us assume it k phi squared. So minus 1 over b partial squared b by partial phi squared equal k phi squared. Or in other words, we can say that partial squared b by partial phi squared plus k phi squared b equals 0. So we have elementary differential equation of phi, which is d squared b over d phi squared plus k phi squared b equals 0. The solution of this function is simply b as a function of phi can be a sine k phi multiplied by phi plus b cosine k phi multiplied by phi. And it should be noted that the magnetic field Hz must be periodic in phi. This means that if I'm rotating around phi a complete cycle, I should return to the same value here. So the function of phi should be periodic in phi. And to be periodic, while it is sine k phi multiplied by phi, the complete cycle of phi here is 2 pi. And effectively, sine n multiplied by 2 pi is periodic function. Similarly, cosine n multiplied by 2 pi is periodic function. This means that the value of k phi must be integer value, such that the function b phi, it would be periodic in the angle phi. So in this case, k phi must be an integer value, or can be assumed the value of n. So we have only one periodic or only one boundary condition here. This boundary condition is that Hz must be periodic in phi, and from this periodicity we introduce that the value of k phi must be integer value. So b phi would be a sine n phi plus b cosine n phi. This is the general solution for the function b as a function of phi. Now, from this boundary condition, we know now that the value of k phi squared can be replaced by n squared. So the other elementary differential equation as a function of rho can be represented as rho squared d squared r over d rho squared plus rho dr over d rho plus rho squared r kc squared rho squared r kc squared equals k phi squared r. So if we are getting k phi squared from the right side to the left side, it would be minus k phi squared r, and this k phi squared is replaced by n squared. So the differential equation of r as a function of rho, it can be represented in this form. Effectively, this form is known as the differential equation of Bessel functions. And the solution of this function, the general solution, this is second order differential equation. So we have two different solutions. These two different solutions are the Bessel function of the first kind, Jn of kc rho, and Yn of kc rho. This is the Bessel function of first kind, Jn, and this is a Bessel function of second kind, Yn. And the general solution of this differential equation as a function of rho is r as a function of rho is a constant c multiplied by Bessel function of order n of first kind of an argument equals kc rho plus another constant d multiplied by Bessel's function of second kind y of order n of an argument kc rho. Okay, where Jn of x and Yn of x are Bessel functions of first and second kinds. From the properties of Bessel function of second kind is that Yn of 0 is infinity or minus infinity. So if the value of d is not 0, then the value of r as a function of rho would be infinity at rho equals 0. This means that we have infinite magnetic field at the center of the waveguide, of the cylindrical waveguide, which is not physically possible. So due to the finite field inside the center of the circular waveguide, the coefficient of the second Bessel function must be 0. That's what we are saying. Yn for any order of n of kc rho becomes infinite at rho equals 0. So to make the field finite along the axis of the circular waveguide, the coefficient d must be 0. So in this case, r is constant multiplied by Bessel function of first kind of order n. So r is a constant multiplied by Bessel function of first kind of order n of an argument kc rho. Now we know r and we already know b. So hz, which is r multiplied by b, can be represented as a coefficient a sine n phi plus b cosine n phi multiplied by another coefficient, so this coefficient is included already in a and b, multiplied by Bessel function of first kind Jn of kc rho. So this is the function of the mode Hz as a function of rho and phi. Now the total magnetic field Hz can be obtained as this mode function multiplied by e to the power minus j beta z. To obtain the coefficients of or to obtain the unknown of Hz, we have the unknown amplitudes A and B, and we have also unknown K cutoff or Kc. What is the value of Kc in the present case? To obtain the value of Kc, we are going to apply the boundary condition. The boundary condition in the present case is that the tangential electric field at the perfect electric conductor or the outer surface of the waveguide should be 0. And the tangential electric field in the present case, we have E rho and E phi. E rho is normal to the surface of the waveguide, but E phi is the tangential. So the boundary condition is that E phi at rho equals A is 0. So E phi at rho equals A is 0. And as we said, E phi from Hz, it would be proportional to the derivative of Hz with respect to rho. So E phi is j omega mu over kc squared partial Hz by partial rho. We already know that Hz is A sine n phi, B cosine n phi multiplied by Bessel function Jn of Kc rho. So the derivative of Hz would be the derivative of the Bessel function, and we are going to assume that, or we make notation for the first derivative of the Bessel function to be J dash. So J dash is the first derivative of the Bessel function of order n. And because here the derivative with respect to rho, so here the argument is Kc rho, so we are going to multiply it by Kc. So we have Kc squared here and Kc in the denominator, so it would be only 1 Kc in the denominator. So E phi as a function of rho, phi, and z from Hz is j omega mu over Kc multiplied by A sine n phi plus B cosine n phi J dash n, which is the first derivative of the Bessel function of first type of order n with an argument K0 multiplied by e to the power minus j beta z. To make A phi equal 0 at rho equal A, this means that J dash n of KCA must be 0. So Jn dash of K0 refers to the first derivative of the Bessel function of order n, Jn of first kind. J is the first kind Bessel function with respect to the arc. And E phi vanish where rho equals A. This means that J dash n of KCA should equal 0. This means that the value of KCA equals the roots of the first derivative of the Bessel function Jn. And effectively, the roots of the first derivatives are called B dash Nm. B dash, B is the root of the Bessel function of order n, and m is the mth root, because we don't have only one root, we have infinite roots. So we have the first root, the second root, the third root, and so on. So b dash nm, it means that it is the mth root of the first derivative of the Bessel function g of order n. So in this case, kca would equal one of these roots, or in other words, we can say that kcnm, the cutoff wave number of the, or the m's cutoff wave number of the n mode, equals b dash nm over a. And actually the values of b dash nm are tabulated as follows. If I'm talking about the mode n equals 0, the first root of the first derivative of the Bessel function J0 is 3.832. The second root is 7.016. The third root, it would be 10.174. If I'm talking about the Bessel function J1, so the root of the first derivative of J1, the first root is 1.841, the second root is 5.331, and the third root is 8.536. In a similar way, for J2 dash Bessel function of order 2, the first derivative has a first root at 3.053, the second root at 6.706, and the third root at 9.970. So these are the mth roots for Jn dash for different n's, and m here is 1, 2, and 3. By knowing the value of the cutoff wave number for the nm mode, we can obtain the cutoff frequency. The cutoff frequency, if cutoff for the mode nm, equals the cutoff wave number over 2 by square root mu epsilon, where mu and epsilon are the parameters or the characteristics of the medium inside the waveguide. So by knowing the cutoff wave number, we can find out the cutoff frequency as b dash nm over 2 by a, where a is the radius of the waveguide, square root mu epsilon. And the propagation wave number beta nm equals square root k squared minus kc squared, and kc squared can be replaced by b dash nm over a squared. Okay? Alright. So now we can obtain the field components for the TE modes in cylindrical waveguides. We have the mode function Hz as a function of rho and phi equals A sine n phi plus B cosine n phi multiplied by Bessel function of first kind of order n, and the argument is Kc rho. If I'm talking about the total magnetic field Hz, this would be the same function multiplied by e to the power minus j beta z. Now we can obtain E rho, E phi, H rho, H phi. Here E rho would be the derivative of Hz with respect to phi. So this would be proportional to the Bessel function. E phi would be proportional to the derivative of the Bessel function or Hz with respect to rho. So this would be proportional to the first derivative of the Bessel function. In a similar way, H rho would be proportional to the derivative of hz with respect to rho, so it will be proportional to the first derivative of the Bessel function. And finally, h of I is proportional to the derivative of hz with respect to phi, so this will be proportional to the Bessel function directly. And the wave impedance in this case, the TE wave impedance for cylindrical waveguide equals E rho over H phi, or minus E phi over H rho, and in both cases it would be omega mu over beta, and omega mu it can be replaced by eta k. Okay, so it is eta k over beta. And as I mentioned before, for any type of closed waveguide, the transverse electric and transverse magnetic wave impedance are the same, has the same formula, eta k over beta for the transverse electric. The only difference is what is the value of beta in terms of the cutoff frequency or cutoff wave number kc. Okay.